Hello everyone, welcome back. In this particular video, we're going to talk about the electrophilic aromatic substitution. This is often abbreviated as EAS. And this is one of the predominant reactions of aromatic compounds. Now, aromatic compounds, now think example benzene and any derivative of benzene, but it's not restricted to benzene and its derivatives. These reactions are applicable to any aromatic compound. So aromatic compounds do not undergo addition reactions unlike their alkene counterparts. What do we mean by that? Now, what we know from before is that alkenes, so think hexene, like a simple alkene that is has some structural similarity to benzene, has a 6-membered ring. If we react this with bromine in a non-coordinating solvent like chloroform, we will get a halogenation reaction. So we get two bromines that are added. Now, just to recapture some of the earlier information, I've shown the stereochemistry. So this addition happens in an anti-fashion. So the stereochemistry here is anti between the two bromines. So this reaction is the halogenation of alkenes. That is what this reaction is. Now that was cyclohexene. Similarly, cyclohexadiene. This would undergo addition reaction with bromine. Again, we would do this reaction in a non-coordinating solvent. So cyclohexadiene with bromine would give us a 1,2 addition product, while also a 1,4 addition product. So these products are defined on the basis of whether the two bromines add to the same pi bond or do they add across this conjugated system. So this is an example of a conjugated diene. So we get the 1,2 addition product and the 1,4 addition product. Now, under these conditions, the 1,2 addition product is the kinetic product, while the 1,4 addition product is a thermodynamic or is the thermodynamic product under these conditions. So both of these molecules undergo these addition reactions using bromine to give us the addition products. But if we try to extend this reaction to benzene, we do not get any reaction. That means we do not get a similar addition of bromine across the pi bonds, although the benzene has 3 pi bonds in it. And so that tells us that benzene, which is an example of an aromatic compound, is not behaving like a regular alkene or even a conjugated diene. It does not behave like it. So there are some differences in reactivity between an aromatic compound and a simple alkene. Now, if to this reaction, I've shown another variation here, if we introduce a little bit of an iron catalyst into this, so some metal catalyst into this, we do get a reaction between benzene and the bromine. But if we look at the product here, this product is not an addition product. It is actually a substitution product, because what happened is the hydrogen that was here was substituted by one of the BRs, and the hydrogen went with the other BR to give us the side product, which is HBr. So under catalytic conditions where catalytic amount of a metal is present, aromatic compounds undergo substitution reactions, unlike alkenes, which undergo addition reactions even without a catalyst. This reaction of aromatic compounds is the electrophilic aromatic substitution. Electrophilic aromatic substitution. So what we're going to do in this video is look at the mechanism of this reaction. In fact, to start off, we're just going to look at the reaction of benzene with a very generalized electrophile. And the mechanism that we learn can be extended to the reaction of benzene or any of its derivatives, which means if there is a substituent on benzene, that same mechanism can be extended to benzene and its derivatives. So for the purposes of introducing the mechanism of an electrophilic aromatic substitution, what we're going to do is we're going to consider the reaction of benzene with a very general electrophile. And what's going to happen in this reaction is one of the hydrogens on the benzene ring here is going to be replaced by the electrophile, and we're going to lose a proton in the process. Now, this proton that is lost is usually captured by a weak nucleophile or a base in the system, a weak base captured by a weak base that is present in the reaction mixture. For the purposes of this mechanism, realize that benzene has 6 hydrogens on it. Okay, there are 6 hydrogens on the benzene molecule, and any of these hydrogens can be replaced by the electrophile. These are all equivalent because benzene is a symmetric molecule. So any of these hydrogens can be used in this reaction. We're just going to use one of these hydrogen atoms. So that's why we're writing out one of the hydrogen atoms like that. And so that we can focus on one of the hydrogen atoms and move on with the reaction. Okay. So as far as the mechanism is concerned, the first step in the mechanism involves a nucleophilic attack by benzene. So nucleophilic attack by benzene on the electrophile. So that's the first step. So because we have an electrophile, benzene has to behave as a nucleophile. So what it does is it uses the pi bond as a nucleophile. Now again, for the purposes of this attack, in principle, you could use any one of these 3 pi bonds. But since we are focusing on this hydrogen, I'm using the pi bond that is adjacent to that hydrogen atom for doing the attack. So when this attack happens, this is going to give us an intermediate. And this intermediate would now have the double bond here, and where the hydrogen is, we are going to have the electrophile bonded to that carbon. Now, since we opened up the pi bond, this is going to give us a carbocation intermediate. This intermediate that we made here, this intermediate is called the sigma complex or an rhenium ion. And a rhenium ion is what this this intermediate is called. And this intermediate, recognize that it is resonance stabilized. Okay, the intermediate, the rhenium ion or the sigma complex is resonance stabilized. So we can draw several resonance forms for this rhenium ion, because what we can do is we can take this pi bond, move it over, and that's going to give us new intermediate here, which, because it is a resonance form of the sigma complex, this is still a sigma complex. And we can do further resonance using the sigma complex, or on this sigma complex where we use the third pi bond or the second pi bond of the sigma complex. So we get a double bond here, and we get a positive charge here. So there is resonance possible in the sigma complex. And in the end, what is possible is that a base, a weak base which is in the system, and it could be any base. Sometimes it could just be the solvent that we are using, but any weak base that is in this system can go and deprotonate this hydrogen. And so that's the hydrogen that we had drawn out initially on the benzene ring. And as that hydrogen is deprotonated, the electrons from this bond fall into that space. And this would give us the product where the hydrogen in the benzene has been substituted by the electrophile that we used in the reaction. So overall, we've done a substitution, and along with this, we're going to get the conjugate acid of the base that we used. Now, this base could have a lone pair on it. It could have a negative charge on it, maybe a stabilized negative charge. And we will get the conjugate acid of the base depending on the nature of the base that we are using here. So overall, we get the substitution product here. Now, some things to recognize here are that if we were to draw a reaction profile diagram for this process, if we were to construct a reaction profile diagram, recognize that we are starting with an aromatic compound. Our starting material here is aromatic, and aromatic compounds are stable, very stable. And in the first step, when the aromatic compound attacks the electrophile to generate the sigma complex, we are losing aromaticity here. The molecule is losing its aromaticity, which means the sigma complex here is going to be a high energy intermediate. So let's say if this is where our starting material is, the aromatic reactant, let's say, if this is where the aromatic reactant is, then the sigma complex, because it is not aromatic anymore, it is going to be very unstable. So that means this is a very uphill process here. So we will get to the sigma complex. And the sigma complex then loses the proton to become aromatic again. Our product is aromatic again. And so the second step here is going to be downhill. Okay, so this is where we have our aromatic product. So we get the aromatic product like that. So overall, what that means is the rate limiting step for this reaction, any electrophilic aromatic substitution, should be this first step when we make the sigma complex. So this would be the rate determining step, because that process would have the highest activation energy. And that is the rate determining step because when we form the sigma complex, the molecule is losing its aromaticity, which means it is becoming less stable. So that makes it the rate determining step of the process. So that is a generalized mechanism of electrophilic aromatic substitution, which can be applied to any reaction where an aromatic compound, now we're using benzene here, but realize that benzene is just an example of an aromatic compound. So any reaction where an aromatic compound is reacting with an electrophilic species, a similar mechanism is what we're going to see. The only difference would be the electrophile and the aromatic compound that we see or that we use in the reaction. But the sequence of events are going to be identical. There would be an initial attack by the aromatic compound on the electrophile to give you a sigma complex, and then in some sense, a collapse of the sigma complex to give you back the aromatic product. I hope you find this mechanism and the discussion useful. Bye.